And that actually plays out fairly accurately. So obviously there's not many choices now, but below 50 is not an auspicious sign, especially if you got below 50 on the first exam, just based on history. So if you're in this range, make sure you're doing all the homework, do it twice, do it 3 times, whatever. Any questions on anything? Not the numbers. Regrade, same typical policy. By hand in by, what's today? 4/14. A written story on the front. So, within a week. Other administrative stuff. Obviously, we have no class on Wednesday. So if you want, I can write a lab just for you. The lab, last week's lab, just hand in next week. The TAs aren't going to be around either. So. Lab, whatever it was, can is due next class. All right, any other questions? Anything administrative or otherwise? Before we journey onward. Does anybody need to register this afternoon? Or is that all out of the way? Okay. So, we were looking at Bode plots. And specifically, last class, we were looking at magnitude plots, which is essentially 20 log magnitude of h. And again, I'll use h of s or h of j omega interchangeably. They're both there. And we considered our straight line approximation. And essentially, the straight line approximation involves find the poles and zeros in each region. We could put quotes around region between sequential poles and zeros, sequential poles / zeros. Find an approximate transfer function. H of s. Draw the line for that region, whatever it is. If it's a constant, it's horizontal. If it's a 1 over s to the n, it has a falling slope of s to the n. Or if it's an s to the n, it has a rising slope of s to the n. Or change the relation slope, I should say. For that region, continue, repeat. And then we could add our little comments there at the end. Add corrections at the poles and zeros. And we recognize that. And then pole is an n times minus 3 dB correction at that pole. And likewise, an n0 is an n times plus 3 dB correction at that 0. Well, I do have some Bode plot paper to hand out, not a lot, so just take 1 sheet, I think, per person. It is on both sides, so you can use that if that's easier. So there's our kind of set of rules for drawing Bode plots for magnitude. And I guess it's worth just doing a quick example problem, something we can throw together fairly fast. But let's throw a little curveball at us, one that's caused some problems in the past. So there's a transfer function. And if we think about this, one thing I should point out, and it's come up already today, it's come up before. Effectively, we can rewrite this as 10s squared, certainly s plus 100. And just to keep things clear, we can write this as 10 s squared, s plus 100, s plus 10 to the 4. Why do I do it like that? Well, I want to emphasize that when we keep the dominant term, when we looked at this last week, when we asked whether s was larger than that polar 0, well, the dominant term is a kind of parentheses concept. So it's stuff we multiply together. So in this case, when we keep dominant terms, that 10 is going to be in every approximate h of s, because it's multiplied by every one. That s squared in the numerator is by itself, so it's also dominant. So in some sense, when we look at each of our regions, the numerator is going to look exactly like that for every region. Because we keep the dominant term in 10 by itself is 10. The dominant term in s squared is s squared. There are no other terms. The dominant term in s plus 100, well, it depends what range of values you're talking about with regard to s. And so we can find our poles and our zeros as part of our checklist. And we have a 0 at 0, which is a double pole. A double 0, sorry. A double 0. And then we have a pole at 100, or 10 to the 2 and 10 to the 4. And so the poles aren't any issue here, but the zeros introduce kind of a new complexity in some sense. As we define our regions, what are our regions? Well, our regions are defined by the sequential series of poles and zeros. But this is AC steady state. Does 0 actually exist in AC steady state? And omega equals 0 is what problem? It's the DC problem. So we have a 0 at 0, yes, but we never talk about 0. If we were going to talk about omega equals 0, we'll do the DC problem. And that's always much easier, as we've seen. So our regions are defined as s less than 100. And notice I don't say greater than 0. It's s less than 100 or omega less than 100. As an AC steady state, it never quite reaches 0, but it does, you can say, approach 0. You know, 10 to the minus 9 hertz is probably a pretty low frequency for most things. Maybe on the galactic scale, maybe that's not low, but we don't worry about that in this class. 10 to the 4, and then 10 to the 4 less than s. So we have 3 regions where we can do our approximations. I'm going to write those again on another paper, give myself some more room. So s less than 100, and h of s in this case is approximately what? Well, again, we keep all the dominant terms. 10 is a dominant term no matter what. So approximately 10 s squared over 100, 10 to the 4. And that's s squared over 10 to the 5, which means what? Well, going back to what we said last week, that's a s squared in the numerator, so that's plus 40 dB per decade slope. Right? That was what we agreed on. No, we don't have a reference, we just know it's plus 40 dB per decade. We could find a reference value by plugging in an omega. So, at omega line approximation, we can break it down a bit. And so, what this means, we have plus N20 dB per decade slope.
Yeah, I see that.
Okay. So this means we have a constant, just to reiterate, it doesn't hurt. constant slope or horizontal flat line of 20 log k. And this means minus n 20 dB per decade slope. And so we could get a reference point out of our approximations, and we know the slope in that region, and so we could use that as a starting point. Typically, I usually use my constant if we have a pass band, then I use that, but we don't always have that. But if we're building a low pass filter or a high pass filter, we do kind of usually have a flattish pass band. In reality, we'll talk about this a little bit next week. Things aren't quite this flat. Any other questions on this? Everybody's good? Now, something to emphasize here, to go back. When we look at a double pole, a double zero at 0, what does that mean? Well, there's an interpretation here. This slope continues off to where? Well, it continues off indefinitely. You know, we said last week beyond Schenectady, which is forever. So that slope continues off indefinitely. So that means if we're drawing from left to right, I mean, we don't have to, but our starting slope, our low frequency slope, is plus 40 dB. So if we have a 0 at 0, that means we have a starting slope. One thing you don't want to do is draw a line here and say, well, there's 0 and then this flattens out. And I bring this up because a lot of people have been confused by this in the past. It's happened on exams. That slope continues indefinitely. We never reach this point. This is minus infinity. So this continues on downward, past Schenectady, past Birmingham, all the way out to Hawaii. It continues, yes. Someplace we'd all rather be right now, sure. So if we have a 0 at 0, our low frequency slope is, if we have a single 0, it's plus 20 dB. If we have a double 0 at 0, it's plus 40 onward. If we have a triple 0 at 0, plus 60 dB. On the same token, if we had a pole at 0, what would that mean our starting slope would be? Negative. If we kind of extrapolated that, what would that mean about our magnitude of our transfer function in the DC case? As omega approaches 0, if we have a pole at 0, what does the transfer function become as omega approaches 0? Infinity. And so can we have a transfer function that's infinite in DC case? No. Though I guess with some of the dependent sources, again, we talked about we could have things blowing up, so theoretically, I guess we could build something like that with dependent sources. So we would have to have active components. So an active component may be unstable in the DC range and become stable as you increase the frequency. So that was a little bit of a summary of what we did in the last class. We visited. Any questions on that before we charge off into phase? What's that? I couldn't. You want this? I couldn't quite hear you. You wanted something? Oh, the 3 possibilities. That one. Okay? These are all different versions of each other. I mean, ultimately, we could say, you know, everything correlates to S to the N, some proportionality, just to write. H of S is approximately S to the N, where N is some integer minus infinity to infinity. And so, where the slope is just n20. So, if n was 0, the slope would be 0, if that line. If n was negative, the slope would be negative. If n was positive, the slope would be positive. So, there are all variations on a theme, but I think it's a little bit more meaningful to see it like this. So, phase. Phase is a little bit different. 40 plots of phase. Remember, this is now linear log. Phase. Log of omega. So, we still break things down into regions, but we have to be a little bit careful. So if we take the same example, h of s equals 10s squared over s plus 100, s plus 10 to the 4th. Ultimately, this is j omega. So yes, we use s a lot. I've said this several times before, but this is really j omega. So if we look at omega equals, 1. Well, ultimately, this winds up being h of s is approximately, or that 10 is out front, and we have j1 squared over j1 plus 100 and j1 plus 10 to the 4. Right? That would be what we would substitute in if we felt like doing this more rigorously mathematically instead of using the straight line approximation. Well, if we consider this an angle situation, what's the angle of this? So if we look at the angle h of j omega, and only the angle terms, what's the angle of 10? And that matters. What is the angle of 10? 0. All right, it doesn't matter much, but we want to be careful here, because we could have a different sign there. That's angle 0. What's the angle of j1? 90 degrees. So that's angle 90 squared. So we got to include that square. That matters. And what's the angle of j1 plus 100? Well, approximately, what is that? It's about angle 0. The 100, the real part, much larger than the imaginary part. In that case, angle of approximately 0. And then angle 0. Well, this is angle 90 squared, but that's multiplication. Squared is something times something, so what do we do with the angle there? This winds up being angle 180. So effectively, just to write things out, we have angle 0 plus angle 180 minus angle 0 minus angle 0. Giving us angle 180. Do we agree? Here we're just looking at the angles. We threw the magnitudes away because we've already done the magnitude plot. So we're just taking out the angles and doing the phasor math that we know. Are we in agreement? And by the same reasoning, we could look at angle h of j10. And I'm going to argue that it's about the same. Angle 0, angle 90 squared, angle 0 goes to angle 180. Anybody in disagreement? So we're good? And I'm going to skip 100 for the moment. I'm going to jump down to angle h of j 10 to the third. Well, the angle of 10 is still 10, or still 0. So that's angle 0. The angle of the numerator doesn't change. 90 squared. What's the angle of this term now? What is the angle of that term? Yeah, j 10 to the third plus 100. Well, I would say j 10 to the third is much, much larger than 100, so approximately what's the angle? About 90. So about the angle 90, and j 10 to the third is much less than 10 to the fourth, so I'd say approximately that's about angle 0. Now I'm off a little bit, maybe enough to bother you, that's fine. Again, this is a straight line approximation, so this is an estimate. You go and smooth things out later. And so where are we? We're at angle 90. So something to note here. We went from 10 to the 2, or 10 to the 1, to 10 to the 3. A pole was at 10 to the 2. What did our angle change by? We crossed the pole, and our angle changed by 90 degrees. That's something that's worth making a note of. So we crossed the pole, and our angle changed by 90 degrees. Backing up a step, at J1, put a little 1 in there because that's what we're talking about. At J1, our angle was 180 degrees. At J10, or omega equals 10, our angle was approximately 180 degrees. If I extrapolated backwards, what if I said J0.1? What do you think my angle is going to be? 180. So if I go, oh, yeah, unfortunately. There's 1, 2, 3. Here's our log omega. 5, 6. That's 10, 10 to the 2, 10 to the 3. There was our pole, remember? There's our other pole. There was our angle. So this is an angle, h of j omega, or phase. And here's my approximate phase for what we've done so far. For less than omega equals 10, our angle is about 180 degrees and constant. We crossed that pole, we went to 10 to the third, and we went down to 90. And so we're about there. Well, since it's a straight line approximation, I'm going to connect those two. And this is where the phase plot is a little bit fuzzier. The magnitude plot straight line approximations are reasonably good. This has some dependencies. In this case, it's not so bad. And so I would say at our pole, which we should be about 135 degrees. But we can check that. So I left room, I skipped the pole, which unfortunately was on the other side of the same piece of paper. So we can look at h, j 10 to the 2. There's our transfer function once again. Angle 0 for the 10. The s squared, that doesn't change. Angle 90 squared. Well, J100 plus 100, this is one you should know by inspection. What's that angle? 45. So that's angle 45. And angle 0 again, giving us angle 135. So at the pole, we have a reasonably accurate approximation of the angle. And that's continuing the steps. And we can look at angle h of j10 to the 4. And again, there's our transfer function. Angle 0 to the 10. Again, this guy doesn't change. Angle 90 squared. And so j10 is much, much larger than 10 to the 2. Or sorry, j10 to the 4 is much, much larger than 10 to the 2. So that's angle 90. And j 10 to the 4 plus 10 to the 4. Again, one we should do by inspection. Angle 45. And that goes to 45 degrees. And we could take it out further. H of j 10 to the 5th. And I'm going to do this fairly quickly. Angle 90 squared, angle 90, angle 90 goes to angle 0. Does everybody agree with that? I mean, essentially it was s squared over s squared. That was our approximation on the previous page. For the magnitude, it's going to be consistent with that. So s squared over s squared is just 1, which has an angle of 0. Here we see it in phase. Then we can go out further. H of j 10 to the 6. Again, angle 0, angle 90 squared, angle 90. You guys don't have to write out every one of these. Yes, you do. Angle 0. Oh, I left out my angles. What about j 10 to the 7? What's the angle going to be as I keep going up in frequency? 0. And so if I turn this back over, there's 0, there's 45, and there's a phase plot, Bode phase plot. Something to note here. In the magnitude plot, crossing a polar 0 changes the slope. In the phase plot, crossing a pole or 0 is an absolute change. So there's our rules for phase Bode plots. Crossing an end pole is a change of phase of minus n 90 degrees. An absolute change. Now here's where things get a little bit fuzzy. It's an absolute change, but how do you draw it? For example, could I do something like this? There's my pole, and then I do that. Is that a reasonable thing to do? So here I drew it kind of linearly over 2 decades, but could I have a sharp drop like that? It's a trick question. It depends on what's making the change. So for now, maybe it's later here in the class, we may consider something that's like this, but most likely on Thursday. But for now, we'll spread our change over 2 decades. That's an approximation, so that depends on the circuit. So in parentheses, I'll say changing over approximately 2 decades. But circuit dependent. In this particular circuit, yeah, it may not be too unreasonable, or whatever circuit generated the transfer function we are looking at. Yeah, that's a reasonable thing to do. We went a 90-degree change, 90 degrees, and then again from here to here, also for minus 90 degrees. There's our pool, and we did that over 2 decades. Beyond that, once we're away from the poles or zeros, the phase is constant. So far less than our lowest pole or 0. In this particular case, phase of 180 degrees. Far larger than our highest pole or 0, phase of 0, and it continues onward. So our phase plots eventually reach a horizontal line, different than our magnitude plots, and I've always found this to be a little bit more confusing. And similarly, crossing and 0 is a change of phase by plus and 90 degrees. And again, that's an absolute change, not a slope change, with the same caveat that it's circuit dependent, changing over approximately 2 decades, but it is circuit dependent. So we'll see situations where that's not accurate. Everybody good? No? Just to throw a little curveball in there, what if I said h of s equals minus 10 s squared over s plus 100 s plus 10 to the 4th? Where does that leave us? What just happened? I'm not sure I understood what you meant. I mean, this part's got to be the same. What is negative sign? What sort of phase is that? Well, we still look at the individual components. Phase of h of j omega. What's the phase of negative 10? Not 0. 180. 180. And now we have 180 up here. And here we have dependencies. Let's say we're looking at omega equals 10, just to make it interesting. So we have angle 0 and angle 0. And that goes to angle 360. What's angle 360? 0. So the phase plot wraps. Which is important. So we could plot the Bodie plot of this guy. It's a terrible Bodie plot, but we're just going to look at the phase. So, what does our phase plot look like? Well, how many zeros do we have? None. Poles, 0, and 10 to the 3, and 10 to the 3 is a triple pole. So at that triple pole, what happens to our phase? That's a change of negative 270 degrees. If I plot this guy, there's my 3 right in the center-ish. 1, 0, 4, 5, 6. Triple pole. Well, for s less than 10 to the 3, what's my phase? Should be able to do by inspection. What's my phase for s less than 10 to the 3? Negative 90. So there's 0, there's minus 90, minus 180, 90, 180, that's a full circle, minus 180 to 80, 180. And so for S less than 10 to the 3. I'm going to say 10 to the 2. We're at minus 90. There's our phase. We cross that pole. What is our phase change by? Minus 270. Where does that put us? Well, that's minus 360, right? Minus 90 minus 270 is minus 360, which is where? 0. And we're going to do this over 2 decades. Is that okay? Is that right? What direction do we move on a pole? We go down, negative. We can wrap. Here's our phase change. This is not correct. You cross the pole, your phase change goes down. You wrap around, minus 180 and 180 are effectively the same thing from a mathematical point of view. So you could wrap it in from the top. If it bothers you, you can go ahead. It doesn't, you're not going to offend anybody that's important. So you could go minus 270, minus 360 in there, and bring it down like this. Well, all I've done is transfer this part up there, so we wrap it on the full circle. That's the same thing. Usually you draw things minus 180 to 180. Those are the bounds. We did that in lab. We found our phase or our phase difference between our source and our measurement. And it was somewhere between minus 180 and 180. Or more strictly in lab, minus 90 and 90. So usually you don't do this all the way down. Wraps around from the top. Something to pay attention to. So similarly, if we cross to 0, you go up, so to speak. So things to pay attention to, things to think about. Everybody good with this? It's a good time for a team assignment. Let's draw some body parts. Disappointed. Not in your answers, the fact that you're not asking. Because if you don't know, you don't ask, where does that leave you? That's a good question. If you can't ask questions, you will be not hired. We'll do it after. No, not double blush. H of S equals S plus 10 to the 2 squared. 10 to the 3, S squared. S plus 10 to the 4. Is this a stable response? Can you build this? A lot of you said yes. Not with passive components. And I said that at the start of class. I gave you the answer. I expected you to write that down and get 2 points for free. Some of you chose not to do. What is our angle? I mean, worst case scenario, even if you don't know how to do the approximations, you can plug in numbers. What are reasonable numbers to plug in? We have pole at 10 to the 4, and 0 double pole, but we don't care about that one per se. And a 0 at 10 to the 2. What's a good number to pick in? Some number far away. Add omega equals 10. What do you get? Well, omega equals 10. What's the angle of the numerator? J10 plus 100. What's the angle of that? Approximately 0. Angle 0 squared. What's angle 0 squared? 0. Angle 0. S squared always by itself. Always. And S always has what angle? S by itself has what angle? Always 90. S is J omega. Which is omega angle 90. By default, S is always angle 90. I mean, you can write that down. It's worth writing down. S is always angle 90. S squared then is what? Angle 180. We did that a bunch of times. 90. What's the angle of this? For tan. Omega equals 10. 0. Also, angle 0. Goes to angle minus 180. Right? We can look at h of j omega, or h of j 10 to the 2. In that case, what's the angle of this now? 10 to the 2. That's angle 45 squared. J 100 plus 100. Yeah.
Just a really quick question. Shouldn't that be angle negative 90 or no? The one
Oh, that was the square. Sorry.
Okay.
It was, I left off the square. Angle 45 squared. Angle 0. This is still angle 90 squared. Angle 0 goes to angle minus 90. Angle h of j 10 to the 3. What's this angle now? Approximately. What is this angle? 90. Angle 90 squared. Angle 0. Angle 90 squared. Angle 0. What's that? That's angle 0. We also crossed the pole. Where was we also crossed a 0. Where was our 0? It was at 10 to the 2. If we cross a 0, what's the absolute change in phase angle? 90 degrees per order. So this was a double 0, right? We have a square. That's a double 0, which I should have written down. You should have said something. Should always indicate that. That was a double 0, so plus 180 degree phase over 2 decades. And so if we go, we draw that. There's our pole, or 0. Say that, 2, 1, 0, 3, 4, 5, 6. This is approximately a change of 180 degrees over 2 decades. Where do we put those 2 decades? Maybe I didn't emphasize this enough. But that's on either side of the 0 or pole. Half on the left, half on the right. So we're at minus 180, minus 90, 0. We start off at 180. There's our 0. There's our pole. That's a double. And that's a single. And so we have a change of 180 degrees over 2 decades. And that fits with what we just did. Here's the straight line approximation, observational way of doing it. Here's the mathematically approximate way of doing it. You can do either one. You can step through the various angles and find out what the phase is at each decade. That's a reasonable thing to do in our problems. In the more sophisticated problems where you have tons of poles and zeros, you're not going to do it by hand anyway. So this is the only type of problem you do by hand. We have a pole at 0. What does that mean? We have a change of 90 degrees, an absolute change of 90 degrees over 2 decades. There's our plot. Is that clear? You can say something if it's not clear. This is the harder part of Bode plots. Most people get magnitude, most people have problems with anything.
Is there any way that we could tell by inspection, to look at the equation, that it can't be built using non-passive components?
If it has a pole at 0 or infinity. So, yeah, there's two possibilities. If h of s, as s goes to 0, is approximately 1 over s to the n, that's not dealt with passive components. And similarly, as h of s, s goes to infinity, approximately s, awesome. Anything that grows without bound. So we can't have anything approaching infinity. So in any case, either of these correspond to h of j omega magnitude going to infinity, in whatever case it is. And so, well, that means the output is infinite times the input, which would be cool, and if you invent that, let me know. And don't tell anyone else. I always wanted to know what the Nobel Prize. Does that answer your question? All right. So, that's transfer functions. What's the thing we haven't put in yet? Circuits. So we built transfer functions for circuits. We looked at transfer functions for body plots, stack them together, and we're done, essentially. Find a circuit, or build a circuit, find the transfer function, take that transfer function, build a body plot. So that's what we're looking at. And so let's look at something a little bit different. So, we have an RC circuit, an amplifier circuit, and an RC circuit. If we think about our nodes, so we can call this VA, call this VB, and our last node, of course, is V out. It's a V. What's VA? So if we call maybe H1 of S equals VA of S over Vn of S. That's a reasonable thing to do. I mean, a transfer function can be defined as anything, right? So if we just define H1 as the voltage at A over the input, that's still a transfer function. What's this transfer function? What type of circuit is that? That's a voltage divider. Does this guy affect this circuit? No. The current going into the op amp for our ideal cases is 0. So that's an RC circuit. Nothing else to worry about there. So we can write this as, well, that's 1 over RC. S plus 1 over RC. With those values are the ones in there. Doesn't matter. And that winds up being 10 to the 3. Over S plus 10 to the 3. Now I skip the steps to derive that, but we've seen that equation a bunch of times. We should be able to kind of write it down by inspection now. Do we agree? No problem. So that's the transfer function VA over Vn. Or in other words, we can write VA of S equals 10 to the 3, S plus 10 to the 3, Vn of S, right? I mean, that's another way, that's where the transfer function came from. It's the ratio of the output over the input. Now with our voltage divider. So that was this guy. We call that H1 of S. Well, let's look at VA and VB. We can call H2 of S equals VB of S over VA of S. What type of circuit is that? It's been a while since we've seen it. What type of circuit is it? It's a non-inverting op-amp. Does this circuit affect VB at all? No. This is an independent circuit, an isolated circuit. And so that's, in this case, 2. If you remember the non-inverting op-amp expression, it's 2. All right, it's a constant, it's fine. And then again, another way of writing this is VB of S equals to VA of S. Again, that's where the definition of the transfer function came from. And this is what we've done all along so far, and the transfer functions are what we're introducing, so it's the same way of writing things out. Well, what about that last circuit? So this we call, this we're calling H2 of S. And what about this guy? So V out relative to VB. Call that H3 of S. What type of circuit is that? It's still a voltage divider, right? So, in this case, it's S over S plus 10 to the 3. We're measuring across the resistor instead of across the cap. And if you don't believe me, prove it to yourself, or we can talk about it. Again, we can write this out. V out of S equals S over S plus 10 to the 3 times VB of S. So there's our V out. Well, we can go back and do substitution. I mean, ignoring our transfer functions for a moment. Well, we know VB is 2 times VA of S. So we can rewrite V out of S equals S over S plus 10 to the 3, put that in parentheses, times 2 VA of S. Right? Let's just substitute in our expression for VB in terms of VA. No problem. And likewise, we can go substitute VA in terms of VN. S plus 10 to the 3 times 2 times 10 to the 3 over S plus 10 to the 3 times VN of S. Do we all agree? Everything's hunky-dory. And now we can rewrite this. This is V out of S equals that. And we can write V out of S over V in of S equals S over S plus 10 to the 3 times 2, 10 to the 3 over S plus 10 to the 3. And lo and behold, what is that? That's our transfer function. And of course, it has to be. And what are these guys? Well, that was H1 of S. That's right, that was H3 of S. That was H2 of S. That was H1 of S. And so, we can write this out using the parts for each isolated stage. The final transfer function is the product of the individual transfer function. This is a 3-stage network. You can add a little H3 in here. This is a 3-stage network, meaning the output of each stage is independent of the next stage. And that brings up 2-port models. Two-port model is essentially just kind of a black box. We have some H1 of X, whatever that circuit is. The in, plus minus. And again, these are oscillating. That's not a DC source. Just draw the plus minus for a reference. And we have the A, plus minus. And then we can have another network. Network is a circuit. Plus minus V out of S. And we can throw a little dot, dot, dot in there. Plus minus, I don't know, VB, whatever the case may be. H4 does. This is a cascaded network. If you can isolate each stage independently, find the transfer function for each stage, they multiply together. That's the moral of the story. If you can do that, of course. So, if we can isolate each stage, then H of S equals H1 of S times H2 of S times dot, 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 H whatever, N of S. If you can isolate each stage. Was that reasonable in the circuit we just looked at? Yes. This circuit is independent of everything that comes after. This circuit is independent of everything on either side. This circuit is independent of what came before. So the circuits are isolated. The output of one stage does not affect the other stage. It cascades. These eventually connect, of course. And so we have an n-stage network. How many stages do we have here? Well, clearly we had 3. Which brings up something to think about for a second. Something we haven't thought about for a while. Again, if we visit our RC circuit, what type of circuit is this? It's been a while. Inverting amplifier. Is that an isolated 2-stage network? It's a trick question. It's a 1-stage network. Why? Well, in this particular case, the inverting amplifier is not isolated with regard to the RC circuit. Why? Current can go this way, and it can go this way. If we do KCL at that node, there's current through R1, there's current through C, and there's current through RA, right? Because the current in the inverting amplifier flows through, in this case, RA, and then to the output through RB. So there is nothing that prevents. So that's not isolated. That's a single-stage network. We'd have to do a little bit of complex algebra, not so bad. Maybe not bad compared to a homework problem. But still, we'd have to do some algebra to figure things out there. Now that said, it may be that you could effectively model this as a 2-stage network. It depends on the relative values of the resistor and the capacitor. We'll come back to that a little bit later. How would I make this? How would I isolate the inverting op-amp? If you looked at the homework, maybe you know. How do we isolate the inverting op-amp from the RC network in the RC circuit? What do we introduce? A buffer. Or more specifically, a voltage follower. How many stages are present now? To be complete, how many stages are present?
3.
There are 3 stages. One of them is trivial, right? We have an H1 of S equals 1 over RC, S plus 1 over RC. It's R1, that's C, that was RA, RB. We have H2 of S equals 1. It's still a stage. It still has important circuit properties. When we talk about ideal amplifiers, we can ignore it. But in reality, a voltage follower will have an impact on the circuit, but it's still a useful tool. So it's a three-stage network, one of our stages being trivial, but it's a three-stage network. And we can multiply things out. H of S then equals 1 over RC, S plus 1 over RC times 1, just include that for fun, minus RB over RA. And we can throw again some components back in there. Maybe make this again 1K, 10 to the minus 6, 1K, 10 to the minus 6, 1K, 1K. And so what do we wind up with? Well, we can plug in those values. Bn then, or H of S then, equals 10 to the 3 over S plus 10 to the 3 times minus 1 times minus 1. Let's change things a bit. Let's make this 2K. Give ourselves a value. Just a quick change. Give ourselves some gain. Oh, yeah, sorry, not a minus 1 there. Sticking too far in. Sorry. So what do we wind up with? Minus 2, 10 to the 3 over S, 10 to the 3. What is this? Circuit-wise. What type of response is this? Or filter-wise? It's a low-pass filter, right? For S less than 10 to the 3, this has a Bode plot that looks something like that. Constant, minus 3 dB correction, minus 20 dB per decade. Do we agree? However, we have a minus 2 here. So just this would be at 0 dB. But we have a gain term. That's a gain term. And I've been using this K all along. That's what I meant by it. K is a gain term. It's the result of an amplifier in this case. What does that mean? For us, our passband now has a value 20 log magnitude of minus 2, which is 2, of course, which corresponds to 6 dB. So if we were to plot this out, that's supposed to be a straight line, 10 to the 3, this is a 6 dB passband. Here would be 0 dB. So our passband has a gain, and it's often a desirable thing. Actually, in communications, it's a vital thing, and it's a lot bigger than 2. So signals get very, very small. You do have active amplifiers, very large amplifiers, which are very tricky to build. And so that has to be large. If you went to the sensor lecture last week, he talked about this a little bit. So the passband, just a second, passband, I think you owe me a couple minutes anyway, always has 20 log of K. And the phase depends on the sign, of course, inverting, not inverting. But the passband level or position is 20 log of K. If we have no amplifier, then we're at 0 dB, like we saw a lot last week, we saw a bit today. If we have an amplifier, well, typically the gain's going to be more than 1, so we move everything up. This is still 20 dB per decade. One last question, I realize you're packing up. What's the value at our pole? What's the magnitude of H and J omega at the pole? What's the correction? -3, so what's our value? We're at 6, what's the correction? -3, so we're at 3 dB at the pole. The fact that they're both 3 is coincidence, it's an artifact of the game. All right.